Okay, we're here to start with inequalities. I suppose when you have an equation, it it has an equal sign in the middle, and it's telling you something very significant, that the left side of that equation is equal to the right side of that equation. When we move into inequalities, it's telling you that they're no longer equal, that there's an inequality. Okay, and the four different symbols that are used in inequalities are listed here. We have greater than or equal to, less than or equal to. Now, if you look at the second, greater than or equal to is just a combination of greater than mixed in with the equal sign. So the number 8 is greater than the number 4, but the number 4 is greater than or equal to 4. Okay, so if it meets one of those kind of conditions, it's either greater than or equal to, well, then it fits in that set. Similarly to less than or equal to, 2 is less than 3, but 3 is less than or equal to 3 because 3 is equal to 3. So it doesn't have to meet both of them, it just has to meet one or the other. Okay, so it's a small difference, but it's a significant difference, and it's important you recognize those, and we'll come across examples of those later on. So when we talk about inequalities, it's important to remember that when we say something is greater than something, it's the left hand side number of the equation that we refer to as being greater than or less than. So for example, when we say 7 is greater than 3, we mean that the 7, which is on the left hand side, and if you look at the actual symbol of greater than, it's wider on the greater than side. So the 7 is facing the big gap, like a crocodile's mouth. The big wide gap, that's the greater than side. Where it narrows down, that's telling you this is the smaller side. Okay, so the bigger side is on the left, the smaller sign of the side of the symbol is on the right, is in the right and at the 3, which is obviously smaller than 7. Same is true of the less than side, and then it's easy when 7 and 3, because you understand that we know intrinsically that 7 is greater than 3. But when you have something like 2x is less than 9, they're telling you that 2 times some number is less than 9. Okay, so the left hand side, which is 2x, is less than the right hand side, which is 9. And again, looking at the shape of the symbol, the narrow part faces the smaller value and the wider part faces the bigger value. So we know, if they're telling us that this is true, we know, for example, that x couldn't be 5 because 2 times 5 wouldn't be less than 9. 4 would be one of the answers because 2 times 4 is less than 9. So what you're basically trying to find, if you're asked to solve this, you'll be trying to find numbers that you could put in instead of x here that make this true. Make this similar to equations that make in this situation the left side less than 9. So then we come to how do we mix inequalities and the number line, because they go together in our syllabus. So the number line, how we go about plotting an inequality on the number line. So showing an inequality, a solution set for an inequality. So we have two distinct groups. We have the sets n, natural numbers, which are positive whole numbers, and z, the set of integers, which are all whole numbers, both positive and negative. Natural numbers start at 1, so 1, 2, 3, 4, 5, and so on. Integers basically is all minus 5, minus 100, plus 70, plus a million, whatever. Okay. We use dots when we're plotting these, anything to do with n or z, we use dots because they're only to do with whole numbers. Okay, the dots tell us what numbers belong in that set. So if there's a dot on the number 2, it means 2 is one of the solutions in the inequality. We put an arrow at the end to show there are more numbers in the set in that direction. So for example, list out all the numbers greater than 5 that are elements that are in the set n, natural numbers. Well, you can't write them all out because there's an infinite number of them. So you might do 3 or 4 and put an arrow at the end and say, listen, there's more that are bigger than 9. I'm not going to put them all in. It's not physically possible. Okay, so this is just a little recap from the book. A natural number is any positive whole number. N equals 1, 2, 3, 4. The dot, dot, dot means there are more numbers up here. We can't write them all down. As natural numbers or whole numbers, to graph them on Numberline, we use shaded dots. So basically, you just put a dot on the numbers that belong to that set. Okay, so if we're asked to show all natural numbers, you would start off with 1, you would stop at 3, 4, 5, and you put an arrow after that. Say, listen, everything passes past this, the set continues on forever. Similarly with integers, dots again, and you see there's an arrow to the left and an arrow to the right when we look at this example of z, because -6, -7, -8, they're all included, and 6, 7 plus 6, 7, 8 are also included. When we come along to real numbers are treated differently, as that set of numbers contains every number imaginable, and there's an infinite amount of those. So if we try to use dots, we would have to draw an infinite number of dots on the number line to represent every single number. So even just between 1 and 2, the numbers 1 and 2, there are an infinite number of numbers in between those two, because we're no longer just talking about whole numbers. So rather than do that, clearly impossible task, we use a thick line, a shaded thick line, to show the set of real numbers on the number line. And the way I always think about lines, especially in coordinate geometry as well, is basically there are an infinite number of dots all kind of blurred together. So there's so many of them, you can't distinguish them anymore, they just end up becoming one solid line. So think of this thick line as an infinite amount of dots all so close together that they blur together into one line. Okay. We still use a dot for sets that are elements of real, that are in the real set, to just show where the set is starting. Okay, you use a dot at the start. So for example, x is less than or equal to 1, you would put a dot on the 1. Okay, so that is where you have greater than or equal to or less than or equal to, and we'll see example 6 down below in a little while. We use a circle, which is basically like a dot without the filled in bit in the middle, to show where the solution set is starting somewhere but doesn't include that exact number. So for example, x is less than 1. If it's a real set, you would put a circle around on the 1, on the number line where 1 is, and then you put your thick line directly beside that below 1. Why do we need that shaded thick line right beside 1? Well, because 0.9999999 is included, which is literally just right beside 1. Okay, and which again we'll do an example down below to show that. And just to recap on real numbers, a real number is any number that can be plotted on a number line, and it's denoted by the set R, and we use a solid continuous shading. With this example here, they've used a red color. It can be black, it can be whatever color, it doesn't make a difference, pencil, as long as it's obvious that this part of the line is included in this and this one isn't. Okay. One little thing about inequalities is when you're multiplying or dividing by a negative number, like you do when you're trying to get x in its own and it might be minus 2x, you might multiply both sides by minus 2. Inequalities, it's a unique situation with inequalities. When you multiply or divide by a negative number, you must flip or reverse the sign, the inequality sign in the middle. And here's just kind of a quick example of why that's true. So 5 is greater than 4. If we decided to multiply both sides by minus 1, they change into minus 5 and minus 4. But the thing in the middle, if you don't move it, this is no longer true. Minus 5 is no longer greater than minus 4. Okay, so minus 5, if it's to the left on a number line, it's less. Okay, it's nothing to do with the number 5 and the number 4. It's where their position is on the number line. So if it's to the left, it's actually smaller or less than. Okay, so that's why we have to flip around the sign in the middle. So we flip around that sign, inequality sign in the middle, and it changes to minus 5 less than minus 4, which we know is true. So this all makes sense when we have numbers and we can see the values and we know that it's logical. But where we have x's or any unknown variables, we have to remember that this rule, we always have to apply this rule, especially when we don't know what the values are each side. Okay, so in the yellow, it just kind of affirms that rule. When we multiply or divide both sides of an inequality by a negative number, we flip or reverse the inequality sign, as well as changing the sign of each term. Okay. So we're just going to go through a couple of examples here. Example 1, draw a number line to show the inequality x is less than 4 and x is an element of n. So again, we have two conditions here that whatever answers we put in must meet. So the numbers have to be less than 4. So straight away we think 3, 2, 1, 0. But then they also have to be part of the set of natural numbers. And we know that natural numbers stop, don't go any lower than 1. So we're just going to put a dot on 1. Okay, and we're just going to use red dots here. And 3. That is the solution set of numbers that fit into this. X is less than 4, x is an element of n. So our solution set is 1, 2, 3. Okay, so there are 3 answers written out as in a list and also shown on the number line. Okay. Example number 2, draw a number line to show the inequality x is greater than or equal to minus 6, where x is an element of z. Now z, as we know, are the integers. So greater than or equal to minus 6. So that is, so you always start with the number that you're given. Is minus 6 greater than or equal to minus 6? Yes, because it's equal to minus 6, so that must be included. And a handy little thing to remember is the inequality sign points you in the direction that the answers are going to be. So it's pointing to the right of minus 6. So that's where my answer is going to be. Minus 5 is also greater than or equal to minus 6. And we keep going and we include all of these. Keep going, keep going, keep going. And we could keep going forever. And we're not going to do that. So we just put a little arrow at the end of my line to show that all of these numbers past 1 are going to be included. Now, we don't need to go up as far as 1. You can decide, normally what you do is you include 3 or 4 numbers and then you stop. There's no need to include a set amount of numbers in your answer. Okay, so if I wanted to write that out as a list, that'd be minus 6, minus 5, minus 4, minus 3, dot, dot, dot. The dot, dot, dot says there are numbers after that that are included, minus 2, minus 1, 0, 1, 2, 3, whatever. Example number 3. Draw a number line to show the inequality minus x is greater than or equal to minus 2. Minus x is greater than or equal to minus 2. The problem we have straight away here is the x has a negative sign. So the first thing we do is we need to multiply. So we have minus x greater than or equal to minus 2. So we need to multiply both sides by minus 1. So that gives us x and 2. And our rule is if we multiply or divide by a negative sign, our sign in the middle must change. So that changes to x is less than or equal to 2. Okay, so then we carry on as normal. X is less than or equal to 2. And remember, x is an element of real. And real is the thick line that we're going to show you. So example 3. So again, we put a dot on 2 because 2 is less than or equal to 2. And again, the inequality is pointing to the left. So we know our answers must be to the left. Okay, so it doesn't have to be amazingly tidy. So whatever numbers we've included on our number line, it's all the way down as far as minus 4, and we put an arrow there. All right. Now it's not possible to list out the solution set for this where it's reals because you'd be writing numbers, an infinite amount of numbers. Okay. So that is how it looks on a solution on a number line. That's the solution set of minus x greater than or equal to minus 2, x is an element of r. Example 4, write down an inequality. So now we're doing the opposite. We're given the number line and we're asked to tell the person, well, what set does this represent? Okay, so we can see here that it starts at 1, so 1 must be part of our answer. It's going to the left, so 0, minus 1, minus 2 are all less than 1. Okay, so x is less than or equal to 1. Okay, it's less than or equal to 1 because they're all to the left side on the number line, and 1 is included, so we have to do the less than or equal to. The question is, what set is this? It is dots, so it can only be either natural numbers or z, which are integers, and because there are negative numbers included, this must be z. x is an element of z. Now you can also alternatively have this down as x less than 2, x is an element of z. Because you would get the exact same answer if it was less than 2. Because again, if it was less than 2, you could only, the next number down is 1. Example 5. Write down an inequality that is represented by the number line shown. We have 1, 2, 3, and 4 dots, and we have an arrow to the right pointing off to the right. Okay, so this is telling us that the set continues on that way. So again, the set is kind of looking up to the right, so that has to have something to do with greater than. So we have x greater than or equal to 1, and x is an element of, they're all positive numbers, so x is an element of n. You could also say x is greater than 0. X is an element of n. Okay, now we could also, these could also be answers for x is an element of z, because natural numbers is a subset of z. N is a subset of z, but we can leave that for the time being. Example 6, write down an inequality that is represented by the number line shown. Now again, this is no longer dot, so it must be x is an element of r. So kind of straight away we can fill in the second bit. X must be an element of r here. The only question is what numbers and what inequality. So the inequality, again, it's pointing off to the left, so it has to be either less than or equal to. And because 1 is included, it has a dot, not a circle, we say that that's x is less than or equal to 1. Okay, so the less than or equal to sign is always a dot. Okay, always a dot when it's the less than or equal to bit. Okay, or similarly greater than or equal to, it's always a dot. Okay, so that's our answer there. And then we look at the example 7. We have a circle on the number 1, so that would mean x is less than 1. X is an element of R. So just a small difference between example 6 and example 7. The only difference is that that inequality sign changes from being less than or equal to with the dot, example 6, and then we have less than, x is less than 1, that is represented by a circle. A circle is telling you that the 1 is not included. The set starts very close to 1 at 0.99999, or infinitely small difference, and it's going off to the left. That's why the less than sign is pointing off to the left. So this is just a quick run through inequalities and how we mix inequalities and number lines. Okay.